Nobody expects the Spanish Inquisition.
And nobody expects another crappy quality video from BYP, but here it is anyway, video number 6 in the Calculate the iMac Tube Power series. In a previous video, I cast significant dispersion on whether my kind of a quick grab of a value for average plate voltage was correct. Whether it was or wasn't, the method was not correct. It turns out the method for finding the average plate voltage is considerably more complicated than that. So, since I've gone to the trouble to figure it all out, I may as well show it to you. And after going through this, you'll see why iMac has the tube computer. It's a lot simpler than this. If they would have simply reduced it to the formula I did and published the formula, that would have been that. But they didn't. Two-part graph. Top portion is plate voltage curve. Bottom is plate current. As previously, the plate current's easy to integrate. Take the maximum times 0.637. That gives the average. Can't do that with the plate voltage on top because the plate voltage is not referenced to the zero line. Integration finds the area under the curve, not over it. And what we need in this case is, for the voltage, we need the area over the curve, and we've got to find that by other means. The maximum voltage is power supply voltage, assumed to be 2 kV. V minimum, in this case, I've changed to a different operating line because I realized the one I had chosen, which ranged from 2 kV down to 350 volts, would have generated 2.45 kW. That's not legal in the US and amateur radio. So I took a much lower operating line, which ranges from 2 kV max down to 1 kV and a maximum current of 200 mils. And that tube is just loafing along, so it'll last forever. It'll still produce roughly kW PEP, and that ought to be enough, especially as band conditions improve. The problem is that it's necessary to integrate the plate voltage curve, but that's offset from zero by the minimum plate voltage, which is a kV. The data from the plate curves is, again, V max is B plus equals 2 kV, V minimum is 1 kV, I max is 0.2 of an amp, I minimum is 0, which, if you recall, the minimum current is on the other side of zero grid voltage. It takes a swing the other direction. There's a complication here. If you happen to notice at the bottom of that graph, 4.5 radians, not pi, not 3.14. In the case for a lower plate voltage and current, that's only a 23 volt grid swing in negative, or cathode swing in a negative direction. The drive signal swings also 10 volts the other direction, so suddenly, with a low drive, the input cycle is not pi radians, it's not half a cycle, it's more than half a cycle. This is not so important for finding a formula for average plate voltage, but that figure will be inaccurate if I use it for this case. For a half cycle, the voltage for the cathode to grid for this 1 kV swing and 0.2 of an amp max plate current is 0 to 23 volts minus. That's from cathode to grid. The other direction, it swings below 0 to plus 10 volts for a total swing of 33 volts. 0 to 23 volts swing is 180 degrees, or we assume so. That's pi radians. In the other direction, it's a proportion of 10 volts to 23 volts times 180 degrees. The result is, adding that, is a total swing of 258 degrees. Now notice if the negative swing goes to 10 volts and the swing the other direction is 10 volts, that defines Class A operation. You won't find that detail in any of the books. The vertical lines under the curves represents the individual vectors from zero current to the line for current, from zero voltage up to the plate voltage for the voltage curve. These are the areas that are integrated. The voltage curve is not integrated above the curve, it's integrated below. So each voltage vector times each current vector equals a power vector, and the integration process, integrating each of those, then multiplying together, gives the total power, and it's very accurate. As before, the current was found by I maximum times the definite integral of sine theta d theta. And recall the sine theta over pi radians, or half a cycle, just ends up being 2 divided by pi, which is 0.637. In this example with low drive, that's integrated up to 4.5 radians, not 3.14, not pi radians. It's more than 180 degrees. So for accuracy, 4.5 has to be used for an upper limit. The integration process for the voltage has to separate that graph into 5 areas. A1, the constant area. That's the area corresponding with the maximum voltage of the lowest plate voltage. Below that area is a rectangle. We don't integrate rectangles. That's a constant. A2 and A3 are what are being integrated to find the average of this curve. Unfortunately, we can't integrate a cosine over pi radians because the result's 0, so it has to be split in 2 vertically and integrated as A2 and then doubled because A3 is also symmetrical. It's the same area on both sides, so integrated over, instead of pi, integrated over pi divided by 2, which is 90 degrees, then double that. A4 is what we think of in the sine or cosine wave as being inside the curve. But again, we can't calculate that directly from this integral. It's got to be the area below the curve, and then we have to add that to the integration of the curve above, which is twice of A2, which will give an average voltage of that curve. That's added to the voltage of A1. That gives the total average voltage for that plate swing. Here, area 1 equals K, a constant, minimum voltage. A2 equals A3. That's the integral of the cosine over half of a half cycle, 90 degrees. A5 is the total area under the curve. I'm sorry, the total area, the total square area, and A4, the area above the curve, is A5 minus A2 plus A3. Now the two side areas, if you will, A2, which is equal to A3, is found by the voltage maximum, 2 kV, minus the voltage minimum, 1 kV, times the integral of from 0 to 4.5 radians divided by 2. That's a little bit erroneous. That's not quite right, but I'll make that up in a minute, of the cosine of the angle. For an interval of 0 to pi, cosine of theta is 0, so we have to go down to doubling A2, which is what the number 2 is, right here, and change the limits of integration from 0 to pi over 2 cosine theta d theta, and then add to it the difference between 4.5 radians, which is a total swing, minus pi. And that last part gives a correction, gives an additional amount for how much that grid cathode voltage swings under 0 as the plate current actually heads to 0. Because for the negative swing up the plate curves, that's current increasing from idle current, which is 62 mils. So in a bit of a formula, we have twice V max minus V min, which is 2 kV minus 1 kV, times the definite integral from 0 to pi over 2, which is 90 degrees, cosine theta d theta. That integral represents 1. Then add in the V min, which is 1000 volts from the tube data sheet. That's the A1 area. The integral above finds the average value of the plate swing. That's added to the minimum voltage, and that gives the total average voltage for that plate swing, and that cannot be found by any other method. Any other way of doing it will result in gross error. So as a formula, we take 2 times the difference in plate voltage swing, V max minus V min, that quantity times 0.637 to get the average. So we're taking the plate voltage swing times 0.637 for an average swing, multiplying that by 2, and adding V minimum. It comes out to be about 1600 volts. Then add the integral for the excess swing with the grid cathode going negative down below the plate curves for the interval between, for theta is greater than pi, up to between 3.14 radians and 4.5, i.e. from pi to 4.5 radians. Now, as the grid swing gets larger, that amount gets smaller, but it never goes away. And it's at the least it'll be a tenth. So it's noticeable. So as a formula, we take the plate swing 2 kV minus 1 kV, which is 1 kV, multiply it by the average conversion, that is 0.637. That obviously gives 637 volts. The minimum plate voltage is 1 kV. Add that together, we get an average plate voltage of 1637 volts. This is confusing and misleading because we tend to think of power by Ohm's law, volts times amps. Well, that's a very high voltage. It ought to be a high power. It would be, except that operating up there close to cutoff means a very low current. So we can't judge power output just by looking at plate voltage. For the current, we take 0.2 of an amp from the plate curves for the 1 kV swing times 0.637 equals 127 milliamp. 1637 volts times 127 milliamps equals 208 watts average, and that is an exact figure. In engineering, that is a defensible figure because I can go back and point to the process wherewith I calculated it, but you can rest assured it's not accurate, because I did not include that extra 10 volt swing. Now, getting down there below 60 milliamp, that's not a lot of power, so it's not going to make a huge difference, but it is there and it does matter. And that will be a little extra dissipation. The thing is, 208 watts over a half cycle is about 100 watts average dissipation. That's a fourth of what this tube is capable of. So this tube will absolutely be loafing along doing almost nothing. And if you recall the Drake TR3 case where the plate dissipation is 52 watts, multiply that by 6 to get the PEP. This will put out several hundred watts PEP and not even break a sweat. So this is good for an initial design and build. If something goes wrong, it's not the plate running at maximum, not having a problem with the output network, and not suddenly overloading the tube and possibly damaging it. You'll basically have to operate this tube into no load to damage it at this drive level, because it's not doing much. It's a 400 watt plate, 400 watt per second. It's dissipating 100 watts. That's nothing. The little horizontal output tubes in a Drake, 6 of them can do that. So there's a big margin of safety when doing this for the first time. Then if more power is wanted, then once the thing is working and everything else is proven, then change it. But don't do what I did initially and start with maximum, because there's no room for error then. And these tubes are too bloody expensive to be making mistakes with. Operating with a higher voltage level might appear to imply higher voltage components, but that's not the case. It actually implies lower voltage components, because what the output network sees is the RF swing, and the RF swing here is only a kV. It's less than what I initially assumed. So the voltage rating for the capacitors, for example, the plate blocking capacitor, where capacitors are rated at DC plus RF swing, that's gone down considerably, and that means the components are a lot cheaper, smaller, lighter, and might just be able to use off-the-shelf components. So there's a run-through of the plate calculations. The grid is the same. The grid's much easier because the voltages both swing the same direction as before. Just take the grid voltage swing and grid current off the graph, find the averages, multiply them together, and that comes out to be a shocking 0.7 of a watt for this drive case. So that brings questions as to whether that's legal under FCC, but if you're a qualified ham, you can figure that out. Kate BYP out.